What is that image? What's it doing? It is a two-lens system, but you can look at the image formed by the first lens, right? So what happens to it? What's going on?
Well, it's a virtual image.
Yeah, it's got to be a virtual image. It's got to be in front of the lens, right? You don't want an object to, you don't want your entire world to look like it's inside the lens. Boy, that'd throw you off. But we can deal with the eye and what it means to the eye. But let's just look at what an image looks like. How a distant object, if you will, gets shifted when you look at it through an optically corrected, or an optical correction device. So, let's put a lens over here, and let's give this lens, I'm going to write it in optical power so that you can figure out what the focal length is for yourself. So let's make it 2 diopters. 2 diopter optical power. And you're looking at an object that is, what's distant? Distant doesn't mean much when you look at the dimension compared to the dimensions of the eye. So about 10 meters away. Make it 20 meters. Make it, 10 meters away. So let's make the object distance 10 meters. Where's the image and, kind of an estimate, what does it look like? This one's kind of bizarre when you think about it, when you actually see it. So first of all, 1 over f implies an f of negative 0.5, right? So about a 20th of this distance. So if this were a half, then this would be about a 1/10 of a half. So you have a focal point somewhere around, maybe there.
You have it as negative?
It's negative, yeah. It's a diffracting or a diverging lens. So we're going to draw, so this would be F. And this is F prime. Remember, they're backwards. So our first principal ray would come in like this. And when it reaches the lens, it's going to diverge as though it started here. So I'm going to just so that's what the first principal ray would look like. And just by looking at the first one, you can see, because of the way this thing is going way out, there's no way the rays are going to diverge or to converge, except for maybe back here. So let's try to keep that semi-straight. It's about impossible for me, but well, what would the second ray look like?
Through the focal point and then back at parallel?
The second ray would go through F prime. Right? Normally, if this were a diverging lens, or a converging lens, it would go through this one to here and then come out parallel. Yeah. Now it's got to go toward this guy to come out parallel. So, to draw it, and it's going to be kind of hard to draw this one. It's going to something like that, give or take. And when it gets here, because it never quite makes it there, then it comes out this way, parallel. Goes through F prime, at least until it reaches the lens, and then it comes out parallel. I'll change colors here so you can kind of see it.
We got this teeny tiny image.
Yeah. So if I work backwards, my image is going to be somewhere close to this focal length, right? Because it's a distant object, but right in about there. And it's going to be limited by this ray right here, this virtual ray. gotta be somewhere inside of this thing here. And then the third ray, if we were to draw that in, and that's gonna be almost parallel. That's gonna come in like this, almost parallel to the second principal ray. And look at that, it works perfectly. Something like that. It goes straight. I had to try to fit it in there, but once
This
it
is
gets,
through the center one?
yeah. You don't go through R because you don't really have a functional R when you have lenses. With mirrors, yes. With lenses, no. So you use parallel through F or through the center. Any two of those three or all three. But in the end, in spite of my horrid drawing,
What do you mean through R? Sorry.
not through R, through the origin. Well, she had asked about R.
What is R?
That would be the radius of curvature for a mirror.
Oh.
At least that's how I first interpreted it. But there's no effective radius of curvature because we could estimate an equivalent set of radii of curvature that would generate this optical power or focal length. But any combination of radii, if they're the right values, will produce the same effect.
So with
And it would depend on
lenses,
the index.
it can go straight through the sensor?
Yes, any ray that goes straight through keeps going. Now, this would reflect back at an equal angle if this were a mirror. But since it's a lens, it goes unimpeded and just keeps going.
Straight through.
Straight through. So in spite of me drawing that horribly, that's about what we would expect. And probably I made this object too tall. It's probably slightly flatter so that this would all go through. I wanted to make it big enough to see. So this is, somewhere in here is where our image is. So what's interesting about this, the way our eye works, and by the way, the focal length, the inverse of the focal length, so the position of the focal length, is the far point of a person who uses those eyeglasses or who uses that lens to see. Right? Because the other term, 1 over O, is infinity. So 1 over I is 1 over F correction, which is your far point. So in other words, this is a distant object, but it's not so distant that it reaches the far point. It's close. So this F here, to the person, if they were wearing these 4 optical corrections, it's putting the world inside this little triangle to see. And then you process that little world. Which I just find amazingly contradicting as an intuition. You got bad eyesight, so you got to make it worse, or not make it worse, but make things even smaller to see. And you think certainly normally think about like microscopes and telescopes to see things better. We blow them up, but in this case, you have to actually shrink it, and that's the most common. Which, by the way, if you look really, really carefully at somebody wearing eyeglasses, their eyes look a little bit smaller, and to a greater degree if they've got really, really strong lenses. So your eyes actually look smaller.
So in old-fashioned glasses, when they're really bad, when you looked at a person wearing them, their eyes would look ridiculous, like oddly proportionate to their head because the lenses would either blow them up or shrink them or, whatever. But it seems like it's not like that anymore. What did they do to the lenses to impact how other people look through
Well,
at you?
There's 2 things I can think of off the top of my head to that answer. First of all, in order to see right, however, whether somebody was grinding it with rocks or whether you had some fancy polishing system to do it like we do it now, your eyes, you're going to have a certain optical power. So as you look through that, it should look the same, all other things being equal. Okay? Now, if the eyeglass is too big, then you're going to see more of a distortion. You're seeing more of the face being shifted compared to what's not being distorted by the lens. Anything else I couldn't necessarily answer. The only other thing I could think is that if the lens were thicker, because it wasn't as good of a material, so they had maybe real drastic curvatures, then maybe just the optical response when you look at it from the side. The thicker the lens, by the way, all these little things matter. The thicker the lens, the smaller the sweet spot. The more drastic the prescription, the smaller the sweet spot. So when you have a really strong prescription, the more you look away from the optical center of the lens, the more distorted and the worse the vision is. So that's one reason why people that get eyeglasses for the first time get headaches, because you have to train your eye to stay pretty close to that optical center. And they usually do that. They take a face and they put your eyeglasses on and figure out where your eye is. And usually they measure that distance. They call that your pupillary distance. They got a little device. In the old days, they'd literally take a meter stick or a small little ruler and stick it up to your nose and measure the distance. You can be off by a centimeter, most cases. And then they put, that's where, if you remove the eyes, that's where the optical center of your lens is. The further you get away from that, the more distorted the image gets when you're looking. Now, it may not matter much for smaller lenses, or it may matter a lot for really strong prescriptions. And in fact, when you look at it off-axis, you get dispersion, just like a prism. And they call that effect prism, or prismatic correction, because sometimes people even need prism in their vision because of something that's intrinsically the matter with their eye. But in a perfect world, you want your optical center to be directly where your eyes are looking out, because it's distant vision. So you take this big old lens, and you got to grind it. You got to grind the outside, and you got to grind the inside. But you want the alignment of the radii, the radiuses of the two faces, to line up on that optical center. So when you cut your lens, when you cut your eyeglasses, you want to make sure that it's right there. Because if it's too far out, you know what happens if your eyes are in here? Not supposed to be cross-eyed, just if your eyes are narrower and your optical center's out there, you'll train your eyes to pull outward, and that'll cause eye strain. Because your eye is going to, over time, position themselves so they get the most clear vision. But if you're pulling your eyes out or pushing them in, then you're going to strain your eyes or make yourself cross-eyed, or look through distorted region of the lens. So all these little practical applications. And it gets even worse when you've got two different axes for the radius of curvature. If it's real steep here, but it's real flat here for astigmatism, then that location of that sweet spot matters even more. And that's probably the first concern for, aside from overcorrection, that's the first concern for bad eyeglasses or for causing headaches with eyeglasses. So you go to get eyeglasses, the first thing they do is they take your prescription and they run it through, put it on a little device that looks like a microscope. And basically what that does is it lines up the radii of curvature, and it shows you where the center of the lens is. And you put a dot there, and then you take it off and make sure that the distance between the dots on the two lenses corresponds to your pupillary distance. And when you put them on, hopefully they correspond to where your eyes are. So I look at your glasses, they're both about a half a centimeter into the center compared to the lenses themselves, because typically glasses extend farther this way. So your eyes are a little inward. And they're also a little lit up, by the way, relative to the center of your lens. Now that one is less of an issue, because it doesn't pull your eyes out this way. You just tend to have to, if you want a clear vision, you tend to tip up a little bit more. But so you don't worry so much about vertical, but you worry about the alignment this way, especially the true distance between them. And if they're too far off, that's a problem. And if you've got really asymmetric eyes, say one eye is here and one eye is here, the way the glasses sit, then you have to not only put that optical center this way, but you have to drop it a little bit on one side. I mean, those are sort of lens maker considerations, but I mean, it becomes more and more complex. It's contact lenses way to go. If you can wear them, ideal way to go. Especially if you're astigmatic and you can wear the more rigid lenses, because they tend to form your lens and sort of push the cornea straight if you have corneal astigmatism. So, yeah, it's kind of fun. Kind of fun to think about. Just a lens problem. Just a lens problem with a little more language. So, we got a little bit of time, got nothing else to do. Any questions about this or the light itself? We can talk about those, or I can give you some more problems. There's a couple things here that are sort of interesting. One of them is the problem of the negative object distance. You take two lenses and you put them together. What happens when the image from the first lens, or the front lens, we'll call the objective lens, focuses an image on the wrong side of the second lens, or on the image side?
We played this last time, I think, because that's what this picture is.
So,
Oh, no, that's not what this picture is.
so we'll just start with a simple lens, kind of like lab. And let's give this lens a focal length. By the way, remember to convert your focal lengths into meters so that they're more conducive to translating into diopters potentially. And alternatively, if you have a lens optical power measured in inverse meters or diopters, then when you take the inverse, it's not going to be in centimeters, it's going to be in meters. And the reason it matters is you want to make sure that your distances, your object image distance, are consistent in language with your focal length value. Right? You don't want to measure focal length in centimeters and have measurements in meters for your object image, because then it's nonsensical. So just some small things to think about. So let's give a first lens with a positive value of, say, 1.10 meters. Okay, so that's a 10 diopter, a plus 10 diopter lens if you were wearing them. I thought of a reason why you might see really distorted eyes. If you were extremely farsighted, instead of adjusting your eye to distant vision, if you're farsighted, you never worry about distant vision anyway, right? It's near vision that's the problem, because you can't accommodate it. So if you get a pair of eyeglasses and adjust it so that you can see up here, you can still see at a distance farther away, potentially. No, that still wouldn't work. You just have to have a lens that, for somebody who's farsighted, adjusted so that you could read, but not necessarily adjusted properly. So it's a little bit off, but your eye can take up the slack. So now the glass may in fact be a more extreme prescription than it might have been before, and so you see this big image because they only have a couple different lenses to give you.
Would it be common for someone who's farsighted to wear bifocals?
More nearsighted, yeah, because your accommodation, you have to accommodate more if you're farsighted than if you're nearsighted. Because you're bringing that image not from infinity, but from beyond infinity, and trying to pull it in here, and then you're trying to do more just to get that extra 4 diopters of accommodation. Okay? So if you're accommodating 6 diopters just to see the distance, add another 4, that's a strain to produce 10 diopters of change. And if your eye can't accomplish that, then you're going to need bifocals or reading glasses sooner than somebody with near vision.
Maybe old lenses, do they used to be curved on both
They were
sides?
curved on both sides. The optical
So the
power
other
should
lenses
change.
will last.
Yeah.
Instead of the magnified both directions. Right?
Yeah, and they were typically used for reading, not so much for distance, because but you wear more likely to read, but you might wear them over time because your eye can adjust in that direction. Okay, so let's put an object somewhere here. So here is semi to scale. So let's put an object here at, say, 15 centimeters. And maybe this thing is 10 centimeters tall. Where's the image formed by this lens? So we can do the calculation, or we can just construct it. If I constructed it, this would be F. This would be F prime, because it's a converging lens. So a parallel ray coming in would be focused to the focal point. A ray coming through F prime would go to the lens, and it would come out reciprocally from the parallel ray. So it's going to come out parallel. I'm wondering how close to. I have a feeling that's not this ray here is not quite steep enough. It's more like that. Try to keep it as scale as possible. Easier said than done for an artistic challenged individual like myself. And then the third ray would go right through the center. And lo and behold, you get your little image over here. So this would be your first image. Now, if I were to take a second lens, I'm over here somewhere and I'm trying to look at whatever that object is. Now, when I first focus that to that first lens and I'm looking through the lens, the image actually appears as though it's on the other side. At least the light coming through the lens does. So I would physically see it out here, but still I need to have my eye lined up with the lens. That's one thing that's kind of weird about it, is I have to look through the lens to see it. But the image that I'm supposedly seeing on the other side is really in front of it. Just freaky. I mean, maybe you noticed that when you were looking at your images on Friday. It's kind of cool. It's neat. It's bizarre. So now, if I were to put a second lens along the optical axis, if I put it over here, then I'm going to have a traditional object distance. But there's no reason why I couldn't put a lens over here. Yeah? What if I put a second lens? Well, what's this distance, by the way? 30 or something, give or take? It's not 30, but it's something larger than 15. So the inverse of 15 subtracted from the inverse of 10.
30 centimeters.
30 centimeters, okay. So this distance here is 30 centimeters. So if I put a lens closer than 30 centimeters, I'm going to have an object, a first object, which is going to be the one, if I'm over here looking, this object is going to be focused again through a second lens. It's going to be as though the object is on this side. Now the reality is all the light that would come here never actually gets there, right? Because of this lens, it never makes it there. So whatever happens over here will produce the final image. Okay, so these rays will then get diffracted as though they came from another, or refracted as though they come from another spot. But you can't, but as we calculate it analytically, we have to solve it as though the object begins over here. Okay, and that's the beauty of this approach, is that it works even though it's a nonsensical scenario. So I'm going to erase this portion of this leg, okay? So I'm going to leave these in place because we'll see what happens to those. And now I'm going to say, well, what if the second lens had a focal length of 5? So F2 has a focal length of 5 centimeters. Okay. And the distance between the two of these is maybe 20 centimeters. And I know that, So I gotta know where to put this guy here, right? So, so the question is, where's the final image? Or alternatively, for the light that's coming from the first lens, where do these rays appear to begin when they come from that second lens? Well, play this game. Since we're at 5, and I'm going to draw this a little bit farther out to make it better to scale, it's going to probably be, if that's 10, it's probably more like there. Just, if you sketched it, you probably sketched it more clearly than I am. We don't have to worry about these rays, but F and F prime are going to be inside here like this. So I'm going to step out for a second and take this image, or this object, as though it's focused from this image, get the principal rays, and figure out where the observer on this side sees that final image. Because that's what you would see if you're looking through these two lenses and you're eyeballing down the lens. Okay? I'll be right back while you're doing that. And we'll first principal ray does what? Comes in parallel,
Comes in parallel.
and it goes through
F prime.
F.
Why?
First one always goes through F, right? Parallel crosses through F. Through F prime comes out parallel, just like this one. So parallel goes through F, through F prime comes out parallel.
So this parallel one is going to look like it's not coming through the lens, but
Okay.
bouncing off of it.
Well, here's what we see. Or as we calculate it, basically it's this ray here, anyway. But we would think about drawing it this way. But what it really means is it's this ray right there
Sure.
coming in parallel, because that's what sets the boundary of the height. Now, where does that ray go? Well, whichever one you look at, what you see is a ray that is bent up through this new F. And this is how I draw it, but this really corresponds to that original parallel ray, because it never makes it over here to converge, it ends up going through the second focal length, or focal point.
So is the other one gonna go through F prime?
Now, the other one, now we got two other things to look at. The other one has to go through F prime. So we would draw it this way.
So it's gonna line up with the other parallel from the first?
And then it comes out parallel, right? And the last one just would go through here. And keep going. In other words, if it were coming in, I'm going to draw the back end of it because it doesn't make sense. In other words, this first ray here corresponds to this ray. Okay? So I'm going to redraw this one as though it were this ray getting to this lens, now coming up like that. This ray, which is as though it were directed towards F prime, is really this ray here, coming from F prime along the direction towards this image, because that's how it's coming in, right? All light coming from here converges here. But now it becomes my new reference line. I wouldn't have known this except for using the second lens, this image, and back tracing it. But this light here, then, if I remove the black, is going to come out parallel this way. Reasonable? And then this ray really corresponds to if light from this object, I know it doesn't make any sense to look at it this way, but remember, light spreads in all directions. We're only taking principal rays and using them for reference. So this ray here would be the reference of a ray coming off of this lens. Okay, so all the rays coming in, it would basically be some ray coming out here that I could not ahead of time have gotten a reference for. But when it comes out, it is directed towards this focal length. And it would then just keep going. So again, it's a clumsy way of looking at it because it just doesn't seem right. But really what it is it's all of this light, and there's a million other ones. Right? There's this entire cornucopia, spectrum of rays coming in here. When it reaches this lens, all of that converge here. But again, we can only use certain rays for reference. A parallel ray, a ray through F prime, and then a ray through the center. So we just have to find them, and the easiest way to do it is to backtrack from the image that's in supposedly negative object distance.
So what's the function of that convergence point then? The one that you had just pointed to?
This one?
Yeah.
That's the image that you see. That's the final image. So when all of this is said and done, it's as though all of this light, which would have come from here originally, gets bent through this first ray as though it would converge here, but it never gets there. And then all that light gets bent and placed through a new point. And so this then becomes my final object, or my final image, excuse me. Some distance away from the second lens. So now we can just do the calculation to make sure that it kind of makes sense and that's consistent. So what should the image be? Should be the inverse of 1/5 minus the inverse of 0.1. Yeah. So it ends up being a plus, which means you're going to have a positive object distance, which makes sense. But it also means that this second image here is a virtual image. Or is it a real image?
same side of the lens as the other image.
It's real. In other words,
It's on the
here's how you
same
think
side
about
as
it.
the
Can I
observer.
take a piece of paper, or can I take a projection screen and place it so that light passing through both lenses produces an image on it? Can I do that?
Yeah.
It's real. I don't know why. But the interesting thing is that the object and the image of this, through the second lens are both oriented the same way. So it's upright with respect to the second lens. So the first image and the second image are the same orientation, but the first image is inverted with respect to the original object. So this one sort of contradicts, where is that third, where can that third image be? I didn't want to necessarily go there. You can have real images, you can have virtual images with a converging lens, but it isn't always the real, the real image isn't always inverted. It's only inverted when the object is on the object side. Right? So this is lens 2. If the second object, or the object for the second lens, if that's on this side, then you're going to get a real inverted image. If the object is on this side, but you're still trying to see it from this side, then the image is going to be upright with respect to the original, to its object. So everything is context. It's the object and image for the second lens, the object and image for the first lens. Well, you could write a paper on just how these things are related, because it's crazy.
So,
Would that first image be considered a real image or a virtual one?
This was a real, it's the first one is virtual. You could not see it unless you took the second lens away. So technically, it's a virtual
So it
image.
is, that's what I was thinking.
Before we
You
put the
can't-
lens there, it's a real image.
You can't put a piece of paper there and see it because the second
Yeah,
lens.
because the lines never actually converge. They're directed as though they would, but they never actually get there because it's that second lens.
so for the lens equation calculation, is there a shortcut so that you don't have to find the first image distance and then use the,
Not that I'm, there's a way, if you know the distance between the lenses and you know the focal lengths, you can derive a straight relationship that will give you how this is related to this. But you gotta piece, the individual magnifications and
like we
the
did
lens
at the end
equation
of the
twice.
lab?
Yeah, so that's at the end of the lab. That actually is how you would do it. So it would require that you know this distance, L, if you will, or D, I forget which one is used in the lab. And if you know this distance, call it O1, then you can figure out what I2 should be with respect to O1. So you absolutely can do that, but it requires some substitution. The easiest thing to do is just get I1, and I1, then whatever that value is, O2 is just L minus I1. And if I1 is bigger than L, then it's going to be a negative number. So then I2 would be 1 over F2 minus 1 over L minus I1, if you will. Because that would be O2.
Yeah, as soon as I get home. Actually, you know what? I'm gonna do this now. Please help prevent CA.
The key to recognize is sometimes you treat an object as though it physically exists,
Okay.
when in fact, because it acts as though it does, but it never actually gets there,
Nonsense.
because you're redirecting the light.